Welcome everybody to today's Power Hour. The focus topic for this month is variable valve timing. Now we've covered VVT in many different sessions in the past year, and so I thought I'd kind of switch it up a little bit, and we're going to talk kind of a new design of VVT, or how General Motors has gone even one step further. Some of you may or may not be familiar with the new 2.7 liter engine. And so today I'm going to talk about the GM 2.7 liter engine and how it affects active fuel management. And we'll talk a little bit about the operation and some diagnostic tips here today. So I'm Ryan Kooiman, Director of Training here at Standard Motor Products. I'm glad to have you with us. Behind the scenes here is our faithful producer, Corey Mayfield. He makes us look good. Imagine how bad I'd look without his assistance here. So yeah, let me head over to the counter, and we're gonna do a little bit of stuff on the truck here today too. All right, so let's get started. So if you're familiar with this engine, or maybe you've not encountered it in your shop yet, this is something that General Motors released or introduced with a 2019 Chevy Silverado 1500. I've got a 2023 truck here in the shop with me today. I've been driving this truck all week. We rented it. I got to start out here by setting the tone and saying I'm very pleasantly surprised and really quite amazed at the drivability of one of these vehicles. When this truck first came out, this was right before COVID, we were going to research and release a new General Motors drivability class. One of my friends works for a builder. He got one of these trucks as a company fleet vehicle. And so he got it, and I'm like, hey, you gotta let me borrow that truck. I need to just spend a Saturday playing with it, taking some pictures. I was blown away at that time at how well this truck performed. So if we look at the torque curve here, I mean, you can see it's pretty steep. Power comes on really quickly. 348 foot-pounds of torque, it flattens out right there. Then we look at the horsepower as it comes on and peaks out at 310 horsepower. Now, I grew up in the 80s. I had a 97 Chevy truck. It was the Vortec 5.7. You know, that was quite something for its day. The 350. I think that thing had like 285 horse. A V8 that's literally more than twice the size of this engine here. So this thing's got a lot of pickup, excuse the pun, but it drives really well. And there's a lot of technology that goes into it. And that's kind of what we're going to focus on today, is all the new technology that GM brought into this thing to really help it out here and make it what it is today. So there's stuff like a dual Volute turbocharger. Now you're going, how many Volutes am I supposed to have on a vehicle here? Well, I'll explain that here in just a second. So it's a different style turbocharger, different internal design. It's got a new evaporative emissions purge pump. And while that's not going to affect the performance of the vehicle, it's going to affect the performance of the evaporative emission system. And because of the turbo, that's why we've got this new EVAP purge pump. I'll explain a little bit more about that. Then this truck has a multi-configuration of valve timing. And so this is going to have variable valve timing, which it will advance and retard each camshaft individually. And then it's got variable lift control, which it's got sleeves on the camshaft which have high and low lift actuation of the valves. And then it's also got active fuel management, so it can kill multiple cylinders at a time. So we're used to seeing that on some 5.3 V8 engines. Now I'm going to tell you that GM's doing it with a 4-cylinder engine. But again, it's very impressive. So now you put this variable valve timing, variable lift timing, and active fuel management together, makes this a really efficient, well-running engine here, but a lot of service opportunities as well. So as I mentioned with that dual Volute turbocharger, we look at the image here and you can see it's got multiple passageways. And what it's really doing is it's helping balance the exhaust flow coming into the turbocharger. So due to the proximity of it, well, think about exhaust headers, right? They're not all the same length. Each tube is wrapped around differently with the goal of scavenging enough exhaust so there's equal passageway before it gets to the common tube there. That's really what's happening with this dual Volute turbo. So if we look at this drawing here, you can see where it's located. Obviously the pathway from cylinders 2 and 3 are much closer or shorter than it would be for 1 and 4. So 2 and 3 are going to share a common passageway, and then 1 and 4 are going to come a little bit longer route, and they're going to be timed perfectly. So the pulsations are going to be constant and perfectly timed to help it improve the efficiency of the operation of the turbocharger on this vehicle. And man, I gotta tell you, it builds boost really quickly. And so this is, I hopped on the expressway with it the other day, very effortless acceleration, getting it up to speed. Now, as I mentioned, there's some changes on the EVAP system. So I'm gonna head over to the drawing here. And as we look at, we've got kind of what seems to be our normal EVAP system. We've got our vent, we've got our purge. So fuel is going to come into the tank here. We've got our fuel tank pressure sensor reading the pressure. It's going to be connected to the vapor canister. We're going to trap or draw in fresh air, whatever is being commanded at the time. So we've got our normally open vent valve. But then we follow the pathway over here to the purge solenoid, which is going to be closed, attached to engine vacuum typically. However, think about this being a turbocharged engine. In a small turbocharged engine, I mean, it's going to be building boost, and we're going to have pressure right here rather than vacuum as we're used to seeing. And so yes, this does go in at the turbo inlet here. That's not a misprint. So in order to prep this for a time when there is vacuum applied on the engine rather than boost, this thing is going to pre-charge the EVAP system. It's going to draw vapor, vacuum, through this purge pump, and then it's going to pressurize the system right here. So we're going to have some pressure pre-charged, and so when the conditions are right, let's say the driver's got their foot off the throttle or it's idling, the purge solenoid can be commanded on, and then the purge gases will be directed into the turbocharger inlet. And so a new component here, a word from friends at dealerships are, they're replacing a lot of these things. By the time they get out of warranty and come into our bays, who knows? But more parts on a system mean more opportunities for us. So hopefully you understand and can appreciate this new componentry added to this particular engine. Now I did us a favor here. I've got some covers pulled off this truck. We're going to take a look at it here in a little bit. However, it takes a little bit of work to get this shot right here. We got all the air intake duct work, and imagine it goes down around the side. On the passenger side, it's connected in by the turbo over there. And so it takes a little bit of work to get that out. So I just took this picture here. Now this isn't like the VVT components I've got sitting on the table here. This is one of the electronically controlled. You know, these are more of a hydraulically controlled system. These are a magnetic solenoid. So if you think about the end of the camshaft or the actuator, the gear on this 2.7 liter engine, it's got basically a button on the solenoid, which think of a ballpoint pen. You click it, it releases it. Now it can change the timing of it. And then it'll click it again to reposition it there. So that's really what's happening on the front of this engine here with these two actuators. These are simply actuating that ballpoint pen, if you will. And now there's a magnetically controlled actuator inside of that. There's actually a technical service bulletin out for that, so maybe after this is a good opportunity to just pull up in service information, 2022, 2023 Silverado. Yeah, aftermarket service information's got really a lot of good coverage on these things already. Look up that technical service bulletin. I just went under VVT or engine mechanical and then look at valve timing and search TSBs. There's some good information stored in there. But then as I mentioned, there's also the variable lift and active fuel management. So in a minute, I'm going to get into this a little bit further, and I'll show you some shots underneath the hood of the truck. There is some scan tool testing we can do. Not as much as what I would hope for necessarily at this point, but I'll show you some examples using some popular aftermarket tools here, stuff we can do if we're testing these things. But if we look at the drawing here, you can see there's the solenoids or the actuators on top here. And as mentioned earlier, we've got a camshaft, which is mostly hollow. Think of a hollow shaft with sleeves attached on top of it. Now those solenoids are going to drop locking pins, which are going to direct those sleeves back and forth, which will give us the actuation for the high lift cam, which is going to be under acceleration, heavy load. But then under light load conditions or idling, now it can go to the low actuation. So if you look at scan data driving one of these vehicles down the road, you'll find quite often the throttle is going to be hung wide open. It'll be in the low actuation mode here, just to help reduce any of the parasitic draw or pumping losses that might occur with a normal engine where the throttle blade is stuck shut. And so it's going to keep it wide open. We're going to get air flowing through there freely, but the manufacturer's controlling the engine speed with ignition timing, with fuel injection amount and timing, as well as the actuation of this. So a lot of different pieces come together to make this engine run extremely efficient, as well as powerful. So let's get into VVT a little bit. Why do it? What's the benefits of advanced valve actuation? So imagine we're engineers, we're designing an engine. A lot of us are gonna go, man, I'm a hot rodder at heart. I want more power, right? Insert the Tim Allen grunt here, more power. But in today's world, emissions come significantly into play. So we've got to balance things out here a little bit. Make sure that we're getting the best performance we can out of the engine, as well as getting, driver comfort, right? We can't have a big lopey cam here. Some of us might think it's cool. Most of our customers aren't going to, though. But then we also have to have good fuel economy, and we have to have clean air coming out the tailpipe at that point. So traditionally, vehicle engine engineers had to balance that out and go, okay, how can I get the best performance out of this cam with the best drivability and the best fuel economy, emissions, et cetera. Well, now enter the new technologies of advanced valve actuation, and really all that stuff's out the window. So as we look at the different types available here, we've got variable valve timing, which it's going to advance or retard the camshafts one way or the other. Advancing it is going to help us get more performance, but retarding it is going to give some valve overlap and help clean up on the emissions side there, give a little bit of internal EGR there. Variable lift, well, if we don't need to open that valve all the way and get a big gulp of fresh air in all the time, we can help with the efficiency of the engine by giving it really just what it needs at that time. And now put them both together, well, it's kind of the best of both worlds here. And we're seeing that on more and more of today's modern engines here. And these are all RPM and engine load sensitive. We don't want to be actuating this stuff and making modern radical changes while the vehicle is idling or light acceleration. Typically it's under open acceleration or steady state cruising down the road where the PCM is going to make a lot of these adjustments here. So some of the big benefits here, first off, is increased volumetric efficiency. It allows it to breathe better. And as I've said before, these engines are primarily an air pump. We're getting air in, we're getting air out. We're creating work with a crankshaft in between there. And so the better we can get air in and out, the more efficient this engine is going to be. And so advanced valve train actuation certainly helps out with that. On the flip side, it's going to reduce those pumping losses. So think about if you get a clogged or a closed throttle blade, it's a restriction on the air intake. Now that's how manufacturers for many years have throttled the engine, right? We close the throttle blade. But as the piston's coming down, we're drawing vacuum. That's a parasitic loss, and that's negatively acting on the crankshaft there. So by keeping that throttle blade open, now we can allow the engine to breathe freer and much more efficient. Think about early diesels. That was one of the big advantages to them. There was no throttle blade, so it made it very efficient. And then on early applications, manufacturers simply eliminated the EGR valve because we get the valve overlap, we could scavenge some of the exhaust into the intake. That would cool down the combustion process and eliminate the need for EGR. Modern vehicles, now we're seeing EGRs come back on so it can further clean the process up. So, as I mentioned, and I showed you this image earlier, this particular engine has control of both the exhaust camshaft and the intake camshaft. Think about some of the early applications of VVT that you may have worked on. For me, I think of the late 90s Ford, like the Escort with, I think it was the Z-Tech engine, not to be confused with the Honda V-Tech, but it was, it controlled the exhaust camshaft. And so that was normally in the full advanced position, and then it would retard it. I think it was up to 17 degrees for that EGR effect there. Well, as other manufacturers came on board with this, they started advancing the intake camshaft for that performance effect. And then we've got engines like this that control both camshafts. It will advance them or retard them. So as we look at some of the examples here, this one being exhaust only, now the exhaust cam is going to be retarded here. And by retarding that exhaust camshaft as related to the crankshaft, now it's going to delay the exhaust valve opening. And so that's going to help retain some of the exhaust gas in the combustion chamber. Now as the intake valve is going to open at its normal time, there's going to be exhaust in there. So we're going to get a little bit of a burst of exhaust in there, and it's going to pull it right back in. It'll stay in the combustion chamber for that EGR effect. Now as we look at intake only systems here, the intake cam will be advanced. And this is going to increase valve overlap. It's also going to have some of that exhaust gas retention. But think about some of the hot rodders in the audience here today. I see a lot of familiar names are logged in here, and I know some of you have played with drag racing back in the days. You know, we used to have gear drives of camshaft, and you're setting up an engine. Is this going to be a round track engine that's going to live at high RPMs? Is this going to be a drag race application? We would set up the camshaft timing a little bit different dependent on the needs of that engine. And so there's benefits of performance to be gained from the intake opening here. Well, over the past 10 years now, we've seen manufacturers using what's referred to as dual equal positioning here. So this is where the exhaust and the intake can be retarded, and then the valves will all be open later here, helping with that exhaust gas retention, or dual independent, which we see on today's engines, such as this 2.7, where they're both going to be retarded and can be advanced here, and it's going to really help with that engine breathing more so than simply emissions. So let's move over into the variable valve lift section here. So we talked about moving the cams forward and backward, but now we're going to talk about opening and closing the exhaust valves and how far do we open those. You may be familiar with this with the Honda systems. They've been using this for many years. Even I think my wife had a 2001 Honda Odyssey with a 3.5. I believe that actually had the valve opening, variable valve opening there. And so as we look at the image here, now under high lift application, which is going to be typically your default, we can see where the valve is going to start opening here at 0 degrees crank. And now as it's being commanded open, it's going to, we can see the lift, the amount of lift as indicated in the blue trace here. But under certain applications, under certain conditions, the powertrain control module is going to command the system to shift. In this case here, it's literally going to slide the camshaft over, and now it's going to apply a low lift opening here. And so this can be done for efficiency. If we don't need all that air in, we don't need all that air out, we can get by with this. Well, that's what the manufacturer is going to use. So as we look at the components here on this variable valve lift system here, we've got, you can see the valve, that's what we're ultimately attempting to control here. And then we've got the dual feed lash adjuster there. And then we've got the inner switchable roller finger follower, which is going to have multiple rollers on it. And then you can see the camshaft there. And that's going to actuate against one or the other here. And many of these are controlled by an oil control valve. And we've got the oil pressure sensor in there, which is going to be a feedback device. As we see that state of oil change, it's going to send oil through a passageway to actuate the system. This pressure sensor is going to be a feedback device saying, yes, I've got oil pressure here, or no, oil pressure has been removed from the system. So now as we put this thing together here, that's what's going to help us achieve that high lift or low lift valve opening based on whichever one is going to be commanded at a particular time. So let's take a look at, this is a snapshot we took of this truck earlier on here. And so as we look at the scan data, you can see my cursor, and this is a snapshot of what was being read at that point in time. So you can see we're cruising down the road here, 54 mile an hour. I'm trying to keep it below that 55 mile an hour speed limit here. You can see a couple times where we blip the throttle. At this point, the throttle's pretty steady. So here's our control solenoid valve command on. So at this point here, we can see the oil pressure. This is the feedback from the system here. And we can see the engine load changing. But if we look further down, you can see as I get in the throttle a bit further, it's going to command this off. And so when this is commanded off, it's going to go to the high lift actuation. And then this is where we see the feedback on the oil pressure increasing at that point there. And so we can see just as the system goes on and off here, this is the changes that's occurring. So again, if I fast forward and we move the cursor over a little bit here, now we can see where the system is commanded off, the oil pressure is going to raise. And so again, think of this is going to really default to off position, which is going to be our high lift system. And so this is going to default, as mentioned, to the high lift system. So when the control solenoid's turned off, we're going to see increased oil pressure there, and it's going to be used again primarily at the higher engine load actuation. That brings us up to a variable displacement. So this is a 2.7 liter engine. Well, not always. That's the max capacity of this engine. So if you think of other V8 or V6 applications, the control module would cut out various cylinders at different times to help improve efficiency. One of the biggest examples of this in recent times has been the 5.3 liter General Motors application here. And so how is that accomplished? Well, first thing is it's going to disable the valve opening, done through various methods, and I'll explain that here in a little bit. But at the same time, we want to disable fuel. Never do we want to disable spark. And I don't think we have a whole lot of control over it, but the engine manufacturers or the vehicle manufacturers don't want to disable spark. We want to get rid of fuel, because imagine if the valves were closed, we're not breathing, we're not taking fresh air in, we're not getting rid of exhaust, but the fuel was continuing to spray. Well, it's going to be a flooded cylinder. You're going to wash the cylinder walls down, you might hydrolock it. So that's why fuel has to be disabled. But who cares if there's still spark there, right? So it's very difficult to turn the ignition on and off, or there's really no need to do that. So it's going to disable the valve opening, which is going to create kind of a cushion as that piston continues going up and down. You might think, well, it's going to drag or it's going to compress. Well, what it does over time is it builds kind of a spring-loaded cushion of air inside there. If you close both valves, now it's going to go down and it's going to have a spring pressure down, and then it's going to have a little bit of resistance, but then on the way up it'll have that opposite effect. And so it kind of equals itself out at that point. So again, if I step over here to the side and if I look at a typical in-cylinder pressure chart, so some of you might be very familiar with this, some of you this might be very new to you, but what we've done here is removed the spark plug. We've threaded in a hose with a pressure transducer. So 0 degrees right here is going to be top dead center. So imagine the piston coming up. So this is building max compression. And now this is where we would have ignition typically. So now we're going to have the power stroke. And so after ignition, it's going to cause that explosion. It's going to force that piston down. So as it comes down, now the exhaust valve will open up. As that piston starts coming up again, it's not going to build the peak pressure like it was over here because that exhaust valve is open. So that exhaust valve open, it kind of plateaus off right here. Before that exhaust valve closes, intake valve opens up. And so now that piston starts coming down again at 360 degrees of crank revolution, right? So we've got 0, 180, 360 degrees of crank revolution. We've got intake open, exhaust closed. And so this is going to be that intake stroke. Now as the piston is coming back down, On the intake, it's going to draw a little bit of vacuum as seen here, and then we're going to start the process all over again. Once that intake valve closes, the piston starts coming up. The 720 mark, or the 0 mark of the next stroke here, we can see it's building compression. So we've got all 4 strokes of the engine operation illustrated right here. So let's do this on one of these engines that's got active fuel management. We can see the strokes occurring here, right? Compression, expansion, or power as it would typically be called, exhaust, intake, and it repeats itself, repeats itself. Now as we kill the valves, what happens? We're still building pressure because the piston's coming up with valves closed, we're going to build pressure there. But we're not seeing that exhaust event, so it's kind of building pressure. It's building pressure, it's building pressure. But you see this trend here, how over time it's kind of settling itself down. And so as it continues to run here, you know, we might have compression, exhaust, compression, exhaust, compression, exhaust. We turn that solenoid or the AFM system off. Now all of a sudden on that exhaust stroke, now the valves work again. And so we're back to our normal 4-stroke operation here. So hopefully you understand a little bit of what happens when that control solenoid is actuated in the system there. So General Motors is one of the most popular applications of active fuel management. Many shops have probably benefited from servicing these things or possibly even deleting them. I've seen a lot of shops do that. Personally, I prefer to put the vehicle back to the way it came. It was built that way for a purpose. And so a lot of service opportunities on working on these things. But as we look at the lifters, on these GM 5.3 example here, you can see the cam lobe on the bottom. It's a roller lifter, so it's actuating or riding on that lifter. Then there's locking pins in there. Those are being commanded open or to be released via oil pressure or hydraulic pressure from the oil there. And so once those pins are released, this lifter is going to collapse against itself and shrink, which is going to have an effect on the valve opening. So this is a picture I took of my father's truck, 2013 Chevy Silverado with a 5.3. He's one of those guys that drives staring at the fuel economy the entire time. So he very much appreciates this mode here. So as I grab my handy Mr. Pointer here, we look at, there's no oil being sent to the lifter in this example. And so the pins are going to be extended, and this is going to be a full-length lifter at this point. And so it's going to actuate and open the rocker, opening the valve here. On this particular one, we've got oil being commanded to it, which is going to release the pins. That lifter is going to collapse against itself, and it's not going to open the valve when it's in V4 mode. So as we look at the manifold, I happen to have one in studio here. Yes, I actually pulled this off a vehicle myself recently. This is one we were doing some testing on for a newer GDI application. You can see where the pump would be located right here. And you can see the multiple solenoids. So in that particular vehicle, it's going to kill cylinders 1, 7, and then 2 and 4. So the outer 2 cylinders on the driver's side and the middle 2. That's going to give the engine some balance there. And so we've got various control solenoids. Then as you look, you're going to see the passageways where the oil will be sent to or returned. So a lot of you might be familiar with that system there. So this GM 2.7 liter here, now again, we put everything together. They're using the variable lift and active fuel management setup here in comparison. Now it's kind of hard for me to explain, but there is these cam sleeves, as I talked about earlier, and now you can see that drawing of the solenoid, and there's 2 pins there. Under proper application or command, it's going to drop one of those 2 pins. And what that pin is going to do, it's going to fall into that little channel there, and you can see that channel is eccentric. It's not straight up and down. And so as that pin drops in there, it's going to cause that sleeve to shift one direction or the other. I can try to explain this all day long, but Corey grabbed a video from the GM website here, explains it way better than I could here. So I'm gonna ask him to quick pull that video up a second, and let's take a look at that. We can see the system inside of the engine. Now under full power, we're gonna have the high lift, but now as that pin has been actuated, you can see that cam slid over there, and it's gonna move it to low lift for steady cruise. Now under the right conditions, it's gonna kill the middle two cylinders. We'll just run on cylinders 1 and 4. But as the driver rolls into the throttle a little bit more, it's gonna reactivate those cylinders, still under low lift mode. And then if the driver really starts to wanna accelerate again, it's going to change it over to the high lift mode, and it's going to give the engine full power. All right, so hopefully that helps you understand a little bit about how this thing works. And so really I want to just kind of share the control layout here. And so we can see on the intake, we've got the multiple components here. And so we've got the solenoids for cylinder number 1, which is going to give us the difference between high lift and low lift. And then cylinder number 2, it's going to give more options, significantly more options. Same with 3 and with 4. So let's take a look over to the truck here. We've got the camera set up, and so let's take a look at some of these components on the truck itself. So we've gone ahead and removed the cover here. There's obviously an engine cover, which is gonna help control the sound. You can see we've got the GDI pump located right here. It's gonna be run off this exhaust camshaft. And so you can see these control solenoids as mentioned. This is those solenoids with the 2 pins. Now the camshafts run underneath here, and then we've got the ignition coils located in the center here. So if you're going to do a tune-up on one of these things, it's really pretty easy to get these ignition coils out. But you can see all these different solenoids located on the engine here. And so you can see that there's, as we showed earlier on the drawing, the intake cam, there's going to be 4 of them. On the exhaust cam, there's only a control solenoid on cylinders number 2 and 3. Okay, so we see some of the components on here. You know, these are, again, really easy to get off. You'll see those 2 different pins in there. But that being said, let me go ahead and start the truck up and pull up a little bit of scan data here. Okay, it's got the truck started there. I'm going to back up. And so I've already built this ahead of time, just trying to keep this down to somewhat of a manageable time frame here. But I went in, I built the vehicle, and now I've gone into the active test mode here. And you can see I can control the exhaust cam position actuator. And then a different version, a few more words of it. And that's one thing that you're gonna have to kind of learn as you go along through these things. If you look up in service information, you look up camshaft actuator, one version is gonna talk about those components I just shared with you on top, which will control the cam sliding sleeves. But if you look at a different avenue of it and you look up VVT, it's gonna talk about the cam actuators on the front. And it's gonna call them the same thing. So you gotta be careful, especially if your service writer is writing a quote or something like that. You gotta find out exactly which one you're talking about. So I'm gonna click on the second option here, the exhaust camshaft position, actuator position. It's kind of like the Department of Redundancy department. And so now we can see the desired cam position is 5.1 degrees. The actual right below it. We can see some more percentages here. As I select increase, you can hear the engine RPM has changed behind me. It's kind of gone to a default 1.6. We can watch our exhaust command percentage on here. And you can see my desired and actual change. So I can ramp this up and down. I can scroll through. I can look at my circuit data. I can see my desired and actuals there as well. I can see that this is synchronized. You know, obviously, if you remember back to one of our earlier sessions, we talked about the importance of cam and crank sensors and the accuracy of those. So a lot of pretty good information here. I still wish I could get a few different commands available from this yet, but again, I'm quite well pleased with what I can see on these ones. And so if you keep, yeah, go ahead and kill the truck there, Corey. You know, so we've got some pretty good diagnostic information here. In a perfect world, I would have a lab scope set up if I'm trying to diagnose one of these. And, you know, so we get pretty decent information there. So to kind of wrap up here in summary, you know, there's a lot of new technology on this vehicle, which means new service opportunities. If I was in the shop yet, I had to really be encouraging my customers to buy these things because there's a lot of stuff on here, which means a lot more stuff to fail. A lot of stuff that's going to keep me in business for years to come here. It's pretty cool, again, how this uses a combination of not just VVT, which we're highlighting this month, but also variable valve lift and active fuel management. So it really puts the three of them together to have improved performance, improved fuel economy, and great tailpipe emissions. So just to kind of wrap things up, I want to remind you again, if you're looking for more information, you can go to our YouTube channel. We've got a great playlist with a ton of different videos here on variable valve timing. We've got teardowns of different systems. We've got cutaways of different systems. We've got a lot of diagnostic techniques available there from our pro training instructors. And so you can even look at our previous power hours. If you've missed some of the ones in the past, you can go there and watch all those. If you're looking for more information or wondering, where can I find that? Go to our Standard Brand website. You can enter in your vehicle. You can look in the catalog there. You can also click on the component tabs there, and you can see right here, we've got a lot of great information on variable valve timing components, the kits, all the great stuff we've got to offer there. So that does it for me here this month. I appreciate you sticking with me. Look forward to being back next month for another great Power Hour topic. But that being said, Corey, I know you've been pretty busy in the background there answering some good questions. Maybe a couple of your favorites here that we want to share?
Absolutely, yeah. So, well, before I get to the questions, first of all, we got quite a few people saying great information. Thank you. And then one I actually like said, I guess we better start getting ready for this. So I'd say the service opportunities you've been talking about is something on their mind. But a couple of really good questions here. One, and I'm kind of curious on your thoughts on this too. What are your thoughts on, say, the longevity of this motor? How long do you think we can expect one of these to last?
Well, my crystal ball's out for repair this week, but again, I like this. I can go off personal references. You know, you think about with the Ford, with the EcoBoost, the 2.7s, the 3.5s, everybody was pretty nervous about those when they first came out. One of my best friends has a fleet of those trucks. They pull man lifts with those things all the time. All of his trucks got over 200,000 miles. Those things have stood the test of time. I expect the same out of this. That being said, my friend whose truck I borrowed 4 or 5 years ago to do the initial research on this, I talked to him recently. He said, hey, how's that thing holding up for you? He said, well, I've had about 130,000 miles and it's been at the dealer for the last 3 months. They were replacing a lot of these timing components there. And somehow it was still under warranty for whatever reason. But, you know, so it sounds like some of those service opportunities are starting to raise their head there. But I look forward to more of this kind of stuff. I mean, engineers are making huge advancements and pumping into today's newer engines. You know, we talk a lot about electric vehicles, but advancements like this is what I think is going to make the internal combustion engine live on well past my career.
That's a great answer. So then the next one would be, and this is more of a broad, but you kind of alluded to the fact that this is not a typical hydraulic VVT system. Can you expand on that just a little bit?
Yeah, and I wish I had some of those components brought here with me today, actually. So when we talk about VVT, you know, typically we're thinking about these control solenoids, which is going to actuate and send oil through a passageway, and it's going to release the locking pin and allow this to phase itself, hence the name cam phaser. The newer ones, well, I hate to call them new because the first one I saw was on a Ford 3-liter Taurus in 2010 already. It uses the camshaft rotation, or the actuation, and also the position of the valve springs to release, if you remember, I talked about that ballpoint pen scenario. The control solenoid is simply an actuator that sticks a peg out and actuates against that actuator to release it. So with these ones, we're using hydraulic pressure. That one, it's simply pressing a button on it, which is going to shuttle this and then create the actuation there. So it's using the rotational torque of the engine. It's not new. You know, we think about VVT as a broader sense. You know, some manufacturers like Nissan have almost a clutch assembly that they're using for that. So there's a lot more to VVT than what we're just showing here today. A lot of different situations and scenarios out there. But good information, or good news for us, a lot of it can be found in service information there. A lot of it's actually covered in many of our classes. So if you're looking to learn more about these systems, you know, we've got some advanced valve actuation pro training classes out there. Talk to one of your stores where you get this stuff, and we'd love to see you in class.
All right. Well, in the spirit of time, I'm going to let you wrap it up and take us out, and thank everybody for being here with us.
Again, thanks, Corey, for helping out here. Thanks, everybody, for tuning in. We look forward to seeing you at the future Power Hours.